now that we have our figures, let's go ahead and graph them out and see what kind of picture we can draw, and from that picture what type of information we can learn. What I'd like to first note is that we have a theta down here and a line, and what this line is representing is the basic ratio between A and B, which if you recall was n, which equaled 5. And so we'll go ahead and pick our arbitrary point. That point we called noon. So here's that point, and so here's that point relative to B and A. Now, the way this graph works is, even though we know B and A exist in relative frames of reference, what this point represents is that shared moment. So imagine like this hand is the relative frames of reference of B, and this is the relative frames of reference of A. What this point's representing is we're going to bring them together and have a point where they not necessarily cross over or touch, but in an analogous way. That's sort of what's happening here, such that you could think of this line as linear time without any relative frames of reference, and in linear time, if there were such a thing, this would be that moment, that present moment at noon, and here's B, and here's A, and that point, again, would be the point 20, 100 with a slope angle that could be accounted for by theta and derived by the ratio of A and B, which is n, 5. So, if we come across here, on our A coordinate, at this point we have A at 100. And if we come down here to our B coordinate, we have B at 20. Now with the Existics equations, what we found and solved for was where A would be relative to B in terms of relative frames of reference, extending away from linear time, if you will. And we found that point to be 104.2211. Let's go ahead and move this A. Actually, let's just do this, give us a little more room here. This is A. And so this point was 104.2211. We'll have it go like this. And so at noon, relative to A, or I'm sorry, okay, and then the other point, before we go there, the other point would be B star, which we found to be 19.1559, something like this. Okay. So, at the time noon, relative to A, since A is ahead of time relative to B, at that time relative to A, when A is 100, B, remember, it was 19.1559, slightly into the past. So we could draw this line up here. So when A is 100, or when A, relative to A, I guess if you will, is at that moment, noon, B relative to B is not quite there, and if there was like sort of a linear time clock, they would be at 19.1559 in their age, working their way towards being 20 at that noon. So then, when B progressively ends up at the same time, noon, now being 20, A has progressed relative to themselves to 104.221. So when B is 20, A is 104.2211. So what we end up with is a couple of different things, but the first thing I'd like to draw attention to is just basically this basic triangle. So when A is remember at noon, I'll go ahead and make this noon. They both share the same birthday, and that's noon of this moment here. So at that moment, when A is there, since A is in faster relative frames of reference, they are slightly ahead of B in time relative to themselves, and B is slightly behind in time relative to A. And so when A is at 100, B is at 19.1559. Then when B works forward to 20, A has progressed to 104.221. So there's a noon relative to A, there's a noon relative to B, and this basically plots out where they are relative to each other. Now, this is what I started with. What I can now do is take this and transdelineate it into a three-dimensional time coordinate system, where instead of having a two-dimensional coordinate system between A and B, what we end up with is a three-dimensional coordinate system between, I guess I'll draw it right here, if you recall, or if you've seen in the video called The Mysteries of Time, I go over my three dimensions of time. And if you remember, we have regular linear time, which is t1, and we have the present, which is more like perpendicular to us or pointing at us. You could think of us as, we're moving along linear time, but we're always in a present moment that's sort of perpendicular to us. So you could think of that as here's t2, and then as we're seeing here, A and B can experience time at different passages of time, and so that third dimension would be t3. So the three dimensions of time are period, present, and passage. Linear time, ever-present moment, if you will, and the passage of the rate of time being able to vary depending on, in special relativity, for instance, depending on your relativistic speed, whether you're moving at speeds that require Lorentz transformation, or if you're near a very massive body, such as time relative to an astronaut versus someone standing on Earth. So, this can turn into that, but before we go there, I just want to point out some interesting facts about this graph that become important pieces of information to know later. Okay, remember the angle theta here. Well, what's really interesting is that even though we've used a continued fraction to slightly modify the values of A and B relative to one another such that they aren't coexisting in a frame of reference that's warped or bent, rather they're in completely separate relative frames of reference that connect, if you will, through an arbitrary set of infinite relative frames of reference, and that's represented by this graph here. So this value that extends away here accounts for the infinite relative frames of reference relative to A. So you could think of it, well, not only think of it, but this is the point B, A star. And then this here is the point B star, A. Again, when A is 100, B is 19.159. When B is 20, A is 104.221. So what's interesting is that the slope angle the hypotenuse of this triangle that accounts for the relative frames of reference, it's the same. It works out to be the same. So if you do the mathematics of, well, let's see here, what can I do? I guess since I have the values here, go ahead and erase these except for I. I'm going to leave that one. Okay. If you take the ratio A over B, you'll find that equals the ratio of n star minus I over u star minus, I'm sorry, I minus u star. So again, what that means is this slope angle is equivalent to this slope angle. This is very important. This comes up later. One thing that this has to do with is in the area where the existics equations and three-dimensional time can be applied to account for the idea of dark matter, rather than having dark matter, the idea is that when we're looking at the galaxies, what we're actually seeing is an extra aspect of relative frames of reference that has to do now, we know, with 3 dimensions of time rather than just 1 dimension of time that can stretch. So what's cool is that here's the ratio without the relative frames of reference, here's the accounting, you know, the ratio created by accounting for the relative frames of reference, and they're equivalent. So this, I'm not going to get into it right now, but this equivalence, if you will, becomes part of the reason why the galaxy appears to be moving all together, even though it has spiraling arms. We've got both, well, okay, so what it is that the parts of the galaxy that are further out, because there's less mass out there, the relative frame of reference, so the passage of time relative to that stuff, is farther into the future than the relative frames of reference of the material more towards the center of the galaxy where there's more gravity. So those things are in a slower relative frames of reference. You apply the existics equations to the time dilation that you would have in a galaxy, and what this equivalent principle makes up for is both the spiraling arms and that everything's, you know, kind of rotating at the same rotational speed. Also, this little slight aheadness and slight behindness goes right along with the data with with CERN's data accounting for the apparent superluminal neutrino prior to them thinking that it has something to do with faulty wires. So this is a very important piece of information that comes out of this graph. And I'm not going to go ahead and transdelineate it into 3-dimensional time yet, because I'm actually saving that for the Wince versus Susskind video, which will be out on March 19th. And so it's in that video that I'm going to start from this graph and then transdelineate it into the 3 dimensions of time, and then derive the vector 6. Why do I keep saying that? Derive the velocity or position 6 vector as a replacement for the velocity or position 4 vector, and how that can be applied to account for a lot of the anomalies in modern physics. Before we move on, something that I'd like to point out and allude to, let me go ahead and erase some of this, clear this up a little bit. If you take the time to work out not just where A and B are at one particular moment, but say, okay, let's leave this ratio of 20 to 1, and let's work all the way back to the beginning. So what this line here represents is that this is when A, if you will, comes in, or I'm sorry, this is when B comes into existence. So this could be like when B is born or at the 0 point, okay? But remember, B has to be greater than 1, so we just, for convenience, what I do is just go ahead and this is the point where B is greater than 1. And again, for those that have issues with the fact that B cannot be less than 1, I direct you to the concept of intermediary relative frames of reference, which deals with this issue quite precisely. And then if you have furthers with that being, if you have issues with that leading to infinitesimals, direct you into my C3 calculus, which you can also find on Existics 101.com. So this is the point of B being greater than or equal to 1, so we'll just go ahead and think of that as some early point in B's initial point of existing. And if you graph all the linear time moments there and then onward, what you end up with are two very interesting curves. And what I'm going to draw is not a very accurate representation of those curves, but it gives you a basic idea, and I highly suggest some of you sit down and play with these equations and work some of this out. All the better way to familiarize with what we're talking about and actually see the potential for its application. When you graph it out, you get sort of a curve like this for A, and a curve like this for B. And so there's sort of like a midpoint, if you will, where the tangent line, there's a tangent line that hits this curve relative to A, and a tangent line that hits this sort of like almost like a slanted bell curve that you get relative to B. And these 2 points appear to be very important. Because at these 2 points, no matter which ratios you use, 20 to 100, 1,000 to 10, whatever, these curves, these tangents to these curves happen near the halfway point to where A and B's relative frames of reference value is around half, such that even though 20 and 100 are not the ratio half, if you progress it forward and keep going, you end up at a point where, because you've added values to 20 and 100, you approach a point where their values are half. And if you just keep going and going and going and going towards infinity, their values approach each other. So what you end up with is an extreme asymptote curve at the initial stage of B, and since A has already been pre-existing, as B just comes into existence, the relative frames of reference really pushes A way far into the future, but there's a strange, and for lack of a better term, inflationary aspect to the relative frames of reference expansion that stays compressed with B until we start to get to a certain point, and then it opens up pretty good so that the relative frames of reference of A and B start to get closer and closer, and then at this point relative to A and this point relative to B, once they've both have passed that point, the relative frames of reference then, as you approach infinity, they approach each other. So what I'm saying is that once you get past these points along these curves in time, no matter which ratio you're dealing with, these, instead of being a triangle like this, they start to basically they go towards becoming an equilateral triangle, and at the limit, it is an equilateral triangle, them basically both equaling infinity and it being the same. So this curve is very important to take note of, and this curve is very important to take note of. Again, applying this to, say, the Big Bang, you could see this as accounting for the inflation period of the Big Bang, and what it is since we're in the future relative to the Big Bang, when we look backwards in time at it, it looks like it has a period where it slows down for a moment, and that could be accounted for possibly by using the Existics relative frames of reference model. Likewise, relative to us, the dark energy may be in the future, and that's why it appears to be accelerating faster and faster and faster as the universe expands. So this curve right here in reverse, which is an interesting thing, may have to do with that. So basically, again, the Existics equations are a tool that can be used where we can now, rather than having to have invariance in certain areas in physics, we can now have variance with conservation laws and start accounting possibly for some of the anomalies in these experiments. For instance, some people have misinterpreted that I'm saying that the Existics equations account for neutrinos being faster than light. Not at all. What the Existics equations predicted was that at some point in the extreme, when we get into extreme aspects of dealing with special relativity, because we don't properly account for infinite relative frames of reference, I believe that there should be some point where the special relativity equations start to fail, and we start having things such as what I predicted, particles appearing to be moving faster than they actually are. So the argument is that the neutrino is not actually going faster than light, it's that it's going close enough to the speed of light, and since it has mass, there's an extra aspect to special relativity that deals with the concept of 3 dimensions of time, that when you apply it, you can have something happen in the way that they did the experiment, where, oh my gosh, it looks like the neutrino is going faster than light, when in fact it isn't. So here are now that we've sort of graphed out some of the stuff you can get by applying the Existics equations, we're going to move on, transdelineate this graph into 3 dimensions of time, and go ahead and at that point actually really start applying the Existics equations to real hard physics.